In section 3.3, we're going to talk about matrices. And so to start off, I'll go through the definition and notation we're going to be using here. First off, a matrix is a rectangular array. A sub ij denotes the entry in the ith row and jth column. And we write the matrix as this rectangular grid array of different entries, again labeled with the subscript notation of I comma j for the ith row and jth column. So we see here this would be like row 1, row 2, row 3, all the way down to row m. And then we have column 1, column 2, all the way over to column n. So this matrix that we're illustrating here is what we call a m by n matrix. Sometimes it's denoted with a bold capital A here to denote the formula for the entry in the ith row and jth column. Sometimes we can also refer to that A sub ij as simply A, and then in brackets we put I comma j. So both of those are equivalent to the different entries within our matrix. It says here that two matrices A and B are equal provided their corresponding entries are equal. Matrices with the same number of rows and columns are referred to as square matrices. So for our first example here, we're going to take this matrix here and do some different evaluations with it. So first off, let's see how many rows and columns we have here. So we have 3 rows and 3 columns. So this is a 3 by 5 matrix. And the first thing says A1, 1, A sub 1, 1. So that refers to the entry in the first row, first column. So that would be 2. And then A1, 2 refers to the entry in the first row, second column. So that would be negative 1. And then our last thing here says the summation I equals 1 to 3 of A sub I. So now we're going to take I start from 1 and count it to 3, adding the entries together. So we start with A sub 1, 1, then A sub 2, 2, and then A sub 3, 3. We add those together. Now if we look in the matrix, A sub 1, 1 is 2, and then A sub 2, 2, that's the second row, second column. That would be a negative 2 here. So plus negative 2. And then the third row, third column, that would be positive 1. So altogether, that would just add up to 1. Now in the next one, it says for the 3 by 4 matrix, given with the entries B of I comma j equal to I minus j, evaluate B to 1, B sub 3, 3, and the summation j equals 1 to 4 of B sub 1, I. Okay, so really we have the formula here given to us, which we can use to find any entry within this matrix. So if we start with B sub 2, 1, then we recognize that I is again the first number in the subscript and j is the second number. So the calculation here would go 2 minus 1, I minus j, so that would just give us equal to 1. B sub 3, 3 would be 3 minus 3, or 0. And then if we want to find the summation, j equals 1 to 4 of B sub 1j, we start off with B sub 1, 1, plus B sub 2, 1, 2, plus B sub 1, 3, plus B sub 1, 4. So the first one would go 1 minus 1, then we'd have 1 minus 2, 1 minus 3, and finally 1 minus 4. So that would be equal to 0 plus negative 1 plus negative 2 plus negative 3. So that would all equal to negative 6. Now what I'd like to illustrate is how we go about constructing the full matrix from the formula that we have. So if we have b of I comma j is equal to I minus j, and it says we have a 3 by 4 matrix, 3 rows, 4 columns, we can lay out the matrix something like this. B sub 1, 1, B sub 2, 1, B sub 3, 1. Then we'd have B sub 1, 2, B sub 2, 2, B sub 3, 2. And then we have B sub 1, 3, 2, 3, and 3, 3. And then lastly 1, 4, 2, 4, 3, 4. That's just listing out the subscript numbers for each of the entries so that we can then go about using the formula to calculate each of them for their numbers. So the first one would be the ij, our 1 and 1, so when we subtract them we get 0. Then we get 1 and 2 in the first column. Then over we get negative 1, 0, 1, negative 2, negative 1, 0, negative 3, negative 2, and negative 1. So again, all I'm doing is, again, I minus j. So in the numbers of the subscripts, subtract them each to get to the numbers in the entries in the matrix. Now we're going to talk about a few different operations on matrices. First off, the sum of two matrices. Two matrices A and B can be added if they are of the same size. That is, they have the same number of rows and columns. The matrix sum is obtained by adding the corresponding entries together. So it's just add the numbers with one matrix with the corresponding entries in the other matrix. Again, they need to be the same size for this to work. And then we have something called the transpose of a matrix, denoted here by a superscript capital T. And so the transpose of a m by n matrix is an n by m matrix whose entry in the ith row and jth column is a sub j I. What this means is the rows switch to columns and the columns switch to rows. So let's look at a few examples of some matrices and how we do the addition and the transpose. First off, we're going to do A plus C. So if we look at the matrix A and the matrix C, they have the same number of rows and columns. They're both 3 by 3 matrices. So to do the matrix sum, we can just add the corresponding entries together. So again, we're looking at matrix A, matrix C. The first number is 2 and 3, so we'll do 2 plus 3, 4 plus 1, 0 plus minus 2. Then down below we have, looks like a negative 1 plus a negative 5, a 3 plus a 0, and a 2 plus 2. Down the last row we have negative 3 from one plus a negative 2 from the other, 1 plus 4, and 2 plus 1. All right, so again, I just took each number from A, added it with the corresponding entry from C. And when I put those numbers together, looks like we're going to get 5, negative 6, negative 5 down the first column, 5, 3, 5, negative 2, 4, 3. Now to do B plus B, we're just going to add the matrix B with itself. So I take the numbers from B, say the 1, 1 plus 1, I get 2. So we get the 2 in the next one below. 2 plus 2 gives us 4. Then we have 4 plus 4, which is 8, first column. Second column looks like I'll have 0, 6, negative 4. Third column, 10, negative 4, 0. And in the fourth column, 6, 2, and 4. Now, to do A transpose, what I'll do with the matrix A is I'll take a row and I will flip it around and make it into the first column of the transpose matrix. So for A, the first row is 2, 4, 0. That becomes the first column of the transpose. So I'll put 2, 4, 0 down vertically in the column here. And then the second row, negative 1, 3, 2. So that'll now turn into the column. And then lastly, the last row, negative 3, 1, 2. I'll put that down the column here. So that's what we call the transpose matrix of A. And if you'd like to give this a practice shot, you can pause the video here and see if you can take A plus C that we found and transpose that matrix. Let's see, the transpose matrix here would go 5, 5, negative 2 down the first column, negative 6, 3, 4 down the second column, negative 5, 5, 3 down the third column. So the next thing we're going to do here is to talk about how a few different operators work with matrices. First off, matrix addition is associative and commutative. As we can see here, either we can group them either way we want to with parentheses, or in the case of a commutative, they can be reversed order with addition. We also have an additive identity, which means there's a zero matrix that can be added, or an additive inverse, which means there's a matrix that when added results in 0. And so addition with matrices works fairly straightforward, what we would assume from regular algebra. Multiplication, however, has a slightly different process to it. We're going to start off first off with scalar multiplication, which basically means if we have a matrix and a constant from the real numbers, then we can multiply the two together by simply taking each entry in the matrix and multiplying it by the constant. In other words, C times A sub ij would be how we do scalar multiplication. The product of two matrices, if we have a matrix that's m by n and another one that's n by p, then the matrix multiplication of the two can be created by doing this summation here, which is a little abstract at the moment. I'll show a concrete example here in a second. But basically, what it's going to mean for us is we're going to take the rows of A and multiply them with the entries in the column of B and add the numbers together. So for this to work, the number of columns in A must match the number of rows in B. We can see that up above when it says m by n and n by p. N is the columns in this matrix, and it's the same as the rows in the other one we're multiplying by. Let's look at our first example here that goes 5a. This means we're just going to take each entry in the matrix and multiply it by 5. So that would look something like 10, 20, 35, and 15. So that's simply scalar multiplication. Now if we multiply two matrices together like A and B, let's write them out here so we can go through the steps. So the way I'm going to do this here is I'm going to take the first row of A and I'm going to multiply each column of B by this. So the way that's going to look, and I'm going to add together the numbers as I go. So first thing I'm going to do is going to multiply 2 times negative 2. And then I'm going to multiply the 7 and the 9 together, but I'm going to add those to the first product. So it'd be plus 7 times 9. That's the first entry. Now I'm going to do the same with the second column. Going to be 2 times 1 plus 7 times negative 5. So those are going to be the first two entries in the product matrix that we get here as a result. Now after I'm done doing that, I'll take the second, do the same thing, take the second column, multiply it times the first, so we're going to multiply the 4 times negative 2 plus 3 times 9, and then we'll multiply the next one over. We'll take the 4, multiply it by the 1, plus the 3 times the negative 5. So as a result here, we're going to have 59, negative 33 on the first row. Then we have 19 and negative 11 down the second row. So that's the result of doing the matrix multiplication here. Now next thing we're going to do the other way around, we're going to do B times A and see if that turns into anything different. So if you'd like to try this on your own, you might want to pause the video and follow along with my first example. We'll take this first row, multiply it times the first column, add the numbers together. So the first one would go negative 2 times 2 plus 1 times 4. We multiply the second column over. It's going to look like negative 2 times 7 plus 1 times 3. And then if we take the second row, do the same with the two columns, we'd have 9 times 2 plus negative 5 times 4. And then 9 times 7 plus negative 5 times 3. So the result we would get here is the matrix 0, negative 2, negative 11, and 48. Now one thing we do notice is here, after doing the multiplication either way, they're not the same. So what that shows to us is that matrix multiplication of this form is not commutative. A times B is not the same as B times A all the time. Now we can multiply a matrix by itself like A squared. That would be the matrix A times itself. So we'd have the matrix 2, 4, 7, 3 times 2, 4, 7, 3. Following the same steps as the last one, if I take the first row, go down the columns like so, we'd get 2 times 2 plus 7 times 4, and 2 times 7 plus 7 times 3. And the second one down below, we take this column, this row, down the next two columns, we get 4 times 2 plus 3 times 4, and 4 times 7 plus 3 times 3. This would give us the matrix 32, 35, 20, and 37. There is a way we can actually connect the matrices to the digraphs and graphs that we had in the last section, and that's through something called an adjacency matrix. An adjacency matrix is a square matrix n by n such that each entry in the matrix, let's call it capital M of ij, is the number of edges from vertex I to vertex j in a graph with n vertices numbered v1, v2, all the way up through Vn. So each entry in our adjacency matrix refers to the connections that we have between different vertices. So what we're going to do here is take this matrix, which we'll consider as the adjacency matrix, and draw the digraph that goes with it. So what I'd like to do first is go ahead and think about what each of these would be numbered as, such as row 1, row 2, row 3, and row 4. Then we have column 1, column 2, column 3, column 4. Now what each of the numbers in my matrix will stand for here are the edges and the number of edges that go between two different vertices. So since we have a 4-row, 4-column matrix, we're going to have 4 vertices in our digraph. We'll label those as V1, V2, V3, and V4. So what I'll do is I'll start out drawing 4 dots, and those will stand for my 4 vertices. So what I'm going to do now is write down the values of each of the entries in my matrix that are not 0. For instance, I have a value in M21, second row, first column is equal to 1. M31 is equal to 1. M41 is equal to 3. Then if I look in the second column, M12 is equal to 1, and M32 is equal to 2. And then finally down in the corner at the 4th row, 4th column, M44, that's equal to 1. Now what each of these numbers is going to tell me to do is the edges I need to draw between which vertices and how many of them I need to draw. So for instance, the first number we have here means we need to draw one edge from V2 to V1. So the 2 and the 1 here are coming from the M21. So I need to draw an edge from V2 to V1. This next one says to draw one edge from V3 to V1. So I'll draw an edge from V3 in the direction of V1. And then the next one says we actually have to draw 3 edges from V4 to V1. So I draw all 3 of these, all going in the same direction. Then this next one down says we need to draw one edge from V1 to V2. Start from V1, draw an edge over to V2. And then this one says we need to draw 2 edges from V3 to V2. So we'll start from V3 and draw 2 edges over to V2. And then lastly, we can have one edge that goes from V4 and loops back around to V4. So once I draw that, now we're done. We've drawn all the different edges as numbered in our adjacency matrix. So in this example, we're going to go back to a digraph we had from the last section and go ahead and draw the adjacency matrix that goes with it. So what I'm going to do here is now first off, list out all the connections we have with our edges. We have an edge that goes from V1 to V2. So for our matrix, that would be in the entry for M12, we have one edge. So we'll have M12 is equal to 1. And if we have an edge here from V1 to V3, then that means the entry in the first row, third column would be equal to 1. We have a vertex from V2 to V3, which means M23 would equal 1. We have an entry from V3 to V4. That would be M34 is equal to 1. we have an edge from V3 to V2, and that's going to be the entry in the matrix of M32, and that's equal to 1 for the one edge. We have an edge from V4 to V1, so M41 is equal to 1. And finally, we have an edge from V4 to V2, and so M42 is equal to 1. Okay, so let's go through each row and column here and fill out. For vertices, we have 4 rows, 4 columns. So first off, we'll locate first row, second column gets a 1. First row, third column gets a 1. Second row, third column gets a 1. Third row, fourth column gets a 1. Third row, second column gets a 1. Fourth row, first column gets a 1. And fourth row, second column gets a 1. And everything else in this matrix would be zeros. So again, the entries we have here are filled out based off of what I've seen in the digraph and the connections between the vertices inside of that digraph.